Okay, all right. So I'm not gonna do a lot of the very basic computing problems. So I'm going to 4.1. This is on page 280. No. 4.1 was 244. Okay. And so there are questions like, does 17 divide each of these numbers? I think you guys can do that on your own. Okay. So let me jump to number 13. So number 13, we are given. Let's sorry. Ooh, what the hell's going on? This. Yeah. Sorry. Okay, so we're given two integers, a and b, and we are told that a is congruent to 4 mod 13, and b is congruent to 9 mod 13. Okay, and we're asked to find the integer, for there is only one integer, c, which is between 0 and 13, such that, and then you have a whole bunch of different questions. Okay, so let me illustrate some of the. I'm always hesitating. I mean, you need to see me do problems, but if I do all of them, then you're not learning anything. You really have to like I say, you have to get your hands dirty and do them. But on the other hand, if you just start from scratch, you might just be tourné à vide. So you need to see me do some stuff.
Sorry, would that be 0 is smaller than C, smaller than 13?
Yeah, it would. Yes, thanks. Not as interesting with a 12. Why did I write 12? I have no idea. Oh yeah, because I was reading less or equal to 12. That's why. Okay. Okay, so let's do A, which is C. We're asked to find C such that C is congruent to 9A mod 13. So I'm going to do that very slowly. Okay, so I'm recording, I'm sharing, my mic is on. Okay, but I don't have the list of people. Okay, I don't know why this just goes away when I share my screen. And I got some more people. All right. Yeah. Okay. So basically, I want to multiply A by 9. Okay. So here we go. So A, we don't know what A is, but it is irrelevant. Okay. Whatever A is, it's not going to make any difference. Okay. So watch this. So A is congruent to 4 mod 13. And we know that we can multiply both sides by the same thing and everything will be fine. So that means that 9a is congruent to 9 times 4 mod 13. So that's fundamental, right? You can add and you can multiply, and this will respect congruences, okay? So 9a is congruent to 36 mod 13, okay? Now 36 mod 13, that's 26 plus 10, right? This is the same as 10 mod 13, right? So 9a is congruent to 10 mod 13. So the number C we are looking for is 10. Okay. Hopefully this is, so there is exactly one number between 0 and 13, strictly less than 13, that will be congruent to 36 mod 13, and that is 10, right? Because 36 is 2 times 13 plus 10. Is everybody okay with this? Yes, excellent. I've got 1 thumbs up, but I'll take that as 2. Ah, yeah, I'm getting likes. Okay, let's do E. So it's the same setup. Let's just scroll down here. Okay, so E is a bit trickier. We want to find C, which is congruent to A squared plus B squared mod 13. Okay. All right, so let's do this. So A is congruent to 4 mod 13. So if I square, I can square both sides. Can I do that? Sure. Right? Because, okay, A is congruent to 4. Let's not write the mod 13. And A is congruent to 4. So I can multiply, right? So A squared is congruent to 4 times 4. So that's legit. So I can square both sides, right? So A squared is congruent to 16 mod 13. Now I can keep it like that, but the advantage of working modulo something is that you can always reduce the numbers at any point that you wish, okay? So I'm going to reduce that immediately. 16 mod 13 is the same as 3. So A squared is congruent to 3 mod 13. Okay, now B is 9 mod 13. B is 9 mod 13. Now, I don't want to use a calculator because I'm like that. I'm lazy. I don't want to get the calculator out. So I need to square that. So 9 squared is 81 mod 13. That's just too big for my little brain. So instead of working with 9, I'm going to work with -4, which is exactly the same thing, right? So why am I doing this? It's just because I'm lazy. Okay. Avoiding the calculator. Now, that's the reason, but also it's faster, right? So B squared is congruent to 16. -4 squared is 16 mod 13. So that's also 3. B squared is 3 mod 13. Okay, so A squared is 3 mod 13. B squared is 3 mod 13. So that means that A squared plus B squared is congruent to 6 mod 13, right? And so the C you're looking for is 6. And that's it. Okay. Now, I'm avoiding the calculator. That's one way of saying it, but it's also a very nice shortcut which can be used even if you have like big machines computing your stuff, right? It doesn't matter. It's the idea that you're taking a little shortcut, and this kind of shortcut is very useful. I wanted to illustrate that. Okay. All right. So if that makes sense to you, hopefully it does, then the other ones should be no. How did you get that A? Yeah, that's the hypothesis. It's given at the beginning. A is 4 mod 13 and B is 9 mod 13. Yep. Okay. So, all right. So the other ones are just exactly the same. I don't think anyone. You have cubes there, but you can also use this trick by reducing, right? Oh yeah. So here's a little observation for F. Same trick. So you want to find C congruent to A cube minus B cube mod 13. Okay, I won't do the whole thing, but just to notice this, right? So A squared, we found that this is 3 mod 13, right? We saw that earlier. So a cubed will be the same as 3a mod 13, and a was 4, so that's 12 mod 13, which is 13, yeah. Which is -1. You can also use you can use -1 if that's relevant. So I can reduce the square first, and then so I don't have to cube the whole thing. You can just do it by little increments, right? And you can do the same. So you can reduce before cubing. Okay, and so if you have big powers, you can split them up. That's actually I mean, this is a non-trivial observation, by the way. So you can split these powers into smaller powers, reduce them first. So you can do reduction before getting huge numbers, right? So this is, and there are many places where you can use these tricks, okay? All right, that's 13. 21 and 25 are, 25 is similar, 27 is similar, 29. So I'm gonna go to 39. So I'm jumping right up to 39. Let's, yeah, okay. I mean, if you have suggestions, I'll do whatever you suggest in that bunch, even if they're like super simple. If you want me to do one, I'll do it. Okay. But I just not, yeah, don't hesitate. Number 39. Okay. So 39 is use exercise 38 to prove that if you have an integer of the form 4k plus 3, if m is 4k plus 3, then it cannot be the sum of two squares. Okay, then m is not the sum of two. Interesting. Two squares. Okay, so no integer of the form 4k plus 3 can be written as the sum of two squares. Okay. All right, so what's 38? What's the statement? When they say use exercise, they mean use the statement, not you don't have to do the exercise to, although I've assigned it because it's actually easier. Is it easier? It's not harder. Okay, so 38 says that for any integer n, n squared is congruent to 0 or 1 mod 4. For every n in Z, n squared is congruent to 0 mod 4, or n squared is congruent to 1 mod 4. And this one I'll leave it to you guys, okay? And the solution is in the, so it's an even number problem, but I've put it in my little document, PDF document. There's, it should be there. The solution is there. Okay, so that's the statement of number 38. And I want to use that to prove 39. So if an integer is of the form 4k plus 3, it is not the sum of two squares. What does 38 say? It says squares are always 0 or 1 mod 4. Okay, so let's see what we can do with this. Okay, so let's take a sum of two squares. Let's say n squared plus k squared. Okay, so this is not my former ploof. I am I am just messing around to see why this would be true, okay? So 38 tells me n squared is either 0 or 1 mod 4, and same for k squared, right? So this could be 0 and 0 mod 4. This could be 0, 1 mod 4. I'm just doing a little table of the possible cases. These are all the cases, right? Okay. For n squared and k squared. So if you add them up, what's the result? Yeah, so let's try something. Let's try to this, and this. Aha. Okay. Right. So I'm looking at everything mod 4. So if n squared is 0 and k squared is 0, what about n squared plus k squared? Well, it'll be 0 mod 4. Yeah, hopefully everybody is okay with that. If n squared is 0 mod 4 and k squared is 1 mod 4, then a squared, you always keep in mind that you can add the right way. Everything will be respected. So this is 1, this is 1, and this is 2, right? So the question 39, sorry, is if m is of the form 4k plus 3, why can't it be the sum of two squares? Well, you see why. Because the sum of two squares will be congruent to either 0, 1, or 2 mod 4. It cannot be congruent to 3 mod 4, which is what this means in the hypothesis, right? So for any squares n squared k squared, n squared plus k squared is congruent to 0, 1, or 2 mod 4, not 3. Okay. So I use the k, and the k which I use here is not the same k. I hope that's okay for everybody. Darn. Okay, let me change the, so if you reread this, I'll use S instead, so it won't be confusing. Okay, so in other words, if m, an integer, is congruent to 3 mod 4, it cannot be the sum of two squares, and the reason is each square is congruent to 0 or 1 mod 4, so if you add them up, you can only get 0, 1, or 2, not 3. Okay, so no integer congruent to 3 mod 4. In other words, of the form 4s plus 3 can be the sum of two squares. Is that okay?
Yeah.
Yeah. Yeah. All right. Good. Excellent. Okay, that's 39. 38, 39, 40, they're all related. They're all, yeah. Okay, 45 is easy. Do I have another one in 4.1? No, 4.3. Ah, I got that's a, I created a cool question. And I actually got the wrong answer when I computed it. I double checked and I had a silly mistake. Okay, so here's a okay, I'm here. 4.3, number 5. That's a small number. Okay, so that's an easy, I mean, it's easy. Yeah, it's an easy question. let's face it, it's an easy question. Yeah, there's something I want to do, which I usually do, but usually there's no pandemic. Is I'm really interested in knowing what you guys are going to be doing next year. Let's assume you're going to pass this course, that you're going to university. So I'm going to I don't know, do a little questionnaire. I don't know how to do it, but anyway. So I'm really curious to know where you guys are going next year. And so yeah, it's coming up.
You can do a poll and
yeah, I know. I have, but if I have to think about it before I start the class.
Or we can just spam the chat.
No.
Everybody scream at once what they're gonna do next year.
Yes. Yeah. There's another thing I want to talk about, but maybe I should. Yeah. Let me pause the recording for a sec, just in case. Okay, number 5, 4.3. Find the prime factorization of 10 factorial. Okay, so that's the question. Find the prime factorization of 10 factorial. Okay, so let's do that. I mean, it's sort of already factored, so it's not much work, but it's kind of cool because it's a big number. Okay, so what is 10 factorial? It is 2 times 3 times 4. I didn't put the 1, right? So 5, 6, 7, 8, 9, 10. So I'm going to factor all these numbers separately. So that's 2 times 3. 4 is 2 squared. 5 is 5. 6 is 2 times 3. 7 is 7. 8 is 2 cubed. 9 is 3 squared. And 10 is 2 times 5. Okay, so I'm done. That's the prime factorization, but that's not the cleanest way to write it. Usually we put the primes together, same primes together. So I'm going to look at 2 here. I've got 1, 2, 3, 4, 5, 6, 7, 8 of them here. So that's 2 power 8. 3, I've got 1, 2, 3, 4. It's 3 power 4. 5, I've got 1 here, 1 here. So that's 2 of them. And what else? There's a 7. Okay, so that's the prime factorization of 10 factorial. Okay, which is nice, not too difficult, right? And then this question occurred to me, so I'm just throwing this question in, and I'm going to add it to my list of questions, I think. Question: what is 10 factorial mod 11? Okay, now obviously you can take a calculator to do this if that's the only thing you're interested in is the answer, but that's not really what we're interested in. Is how do you get 10 factorial mod 11 if you are on a desert island and for some reason the food is in a box, and to open the box you need to compute 10 factorial mod 11, and you didn't bring your calculator to this desert island. Okay, so
Sir, I have a question.
yes.
So, okay, I might be slow on this one, but basically, like mod 11, it's as if we did like on Java, like 10 factorial remainder of 11.
Yes.
Okay.
That's it.
Okay, yeah.
Yeah. So you divide by 11, you look at the remainder. That's exactly it. Yes. Okay. But what I want to show you is how I would do it, how I reason it out. Again, if you think only in terms of these smallish numbers, it's not so interesting, but it's more the principle of the thing. It's getting used to reducing before doing big computations. Okay. So I'm reducing 2 power 8 times 3 power 4 times 5 squared times 7 mod 11. That's what I want. Okay, so 2 power 8 times 3 power 4 times 5 squared times 7. Okay, I'm going to reduce the factors separately, which I can, right? We know that this behaves well. So look, let's just write this. So 2 power 8 is the same as 2 power 4 times 2 power 4. 3 power 4 is 9 times 9, right? I'll just write it this way, 3 squared, 3 squared. 5 squared, 25 mod 11, right? So let's just add this here. 25 is 22 plus 3, right? So this is congruent to 3 mod 11. That's obvious, easy, right? So I'm just going to put a 3 here times 7 mod 11. Okay. 16 mod 11. 16, that's congruent to 5 mod 11, right? So this is 5 times 5. 9 is minus 2 mod 11. So I'm just messing around with the numbers to make them as small as I can, right? That's what I'm doing. Okay. So I'm working mod 11. So 9 is the same as minus 2, right? Okay, so 5 times 5 we said was 3 mod 11. So this is just 3. Minus 2 times minus 2 is 4. Times 3 times 7 mod 11. Okay. And well, at this point it's getting small, but I mean, why not? Let's just keep on going. 3 times 4 is 12 mod 11. That's 1, right? 12 is congruent to 1 mod 11. So this here is just 1. So this is the same as 3 times 7 mod 11. And 21 mod 11, that's 22 minus 1, that's minus 1. So it's 10 mod 11. Right. And so the answer, 10 factorial mod 11. Remember, if it's underlined or bold, it's the function mod, which is the remainder of the division. So this is 10. Okay, so I wanted to illustrate again. It's the same. I mean, I'm doing a lot of that, but it's very useful to reduce bits and pieces before you take big powers or multiply or add or anything. You can just work. See, I didn't use any. I mean, all the calculations here were really small, very, 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 very small. Okay, so hopefully you see that this is working out. Right. This. Yep.
I know it's a bit like a dumb question, but what's the difference in what would be the difference in the underline and just the regular mod 11? Like when you write it out.
Sorry, say that again. You're asking.
The difference between when you underline the function mod 11 and when you just write a constant.
Yeah. Okay. So one is a function. So if I write mod m and I put something here, that's my input. And this whole thing is the remainder of division of input by m. Okay, when you're doing the division algorithm. Okay, so 15 mod 7, this is 1. Okay, so it's an integer. It's a mod function. It takes 2 inputs and it outputs an integer. If I write a congruent to b mod m, this is a relationship between two numbers a and b. Okay, this is so this whole thing is one single relation. It was notation. This is just, this whole thing is the notation for a binary relation between, so it's a relation between two integers. A and B are related by this binary relation when their difference is divisible by m. Okay, we could write it, you know, an alternative notation would be this. We could write it like that. We could say A is congruent to B mod m. We could write it this way. Maybe there would be less confusion.
No, it's all right. Thank you, sir.
Yeah, so underline is the function, not underline is a symbol in the notation for a relation. It's not a value, okay? So when if I write, you know, 12 is congruent to 5 mod 7, it's a relationship between 2 and 5. This is, so it's either yes or no. Either this is true or false. It's a relation. Predicate.
Yeah, because
It's like equality.
Yeah.
It's just a generalized form of equality, but it's just like there's a lot of symbols for it, right? Because for each m, there's a different kind of equality, if you want.
thank you, sir.
Yeah, it's just, yeah, I know. But if it helps, it's read it in your head. A is congruent to B. I mean, if you say it out loud or in your head, if you don't, you know, it helps. It helps. Okay. Let's say, oops, sorry, microphone. Yeah, I looked at number 47. That's a nasty question when you just look at it like that. But it turns out that if you just spend time with it a little bit, one after another, it's not so bad. But maybe I can show you 47. 47. Which one is an interesting one? E, maybe E. So you're given a sequence and you're asked to describe that sequence or the nth term of the sequence. And the hint is that it's related to prime numbers. Okay, so 47E is the following sequence: 1, 2, 3, 3, 5, 5, 7, 7, 7, 7, 11, 11, 13, 13, just keeps on going like that. So what is a n in general? Hint has to do with prime numbers. Okay. So, I mean, you look at this sequence here, the first one is sort of misleading, but the first term is not really interesting. You can actually start over here, and that's makes a bit more sense. But if you, I mean, obviously the terms of this sequence are all prime numbers and they're growing. So you got 2, then 3, 3, then 5, 5, 7, 7,
Is
7,
it
7. Yep.
like the je vais le dire en français parce que j'ai pas le mot là, genre l'écart entre les nombres premiers, genre entre 2 puis 3, il y a 1, après ça entre 3 puis 5, il y a 2, fait que pour ça, il y a 2, 3. entre 5 puis 7, il y a 2, 5. Entre 7 puis 11, il y en a 4, fait qu'il y a 4, 7. 11,
Basically, it
13.
repeats the last found prime number until it finds another one.
Yeah.
Ouais, dans le fond. Merci, Jacob.
So, well, it's interesting though. Is your so you're saying is it this? No, but wait, it can't. You're saying can it be the distance between?
The difference between two prime numbers. So let's say between 11 and 7, you do, let's say 11 minus 7, there's 4. So 7 is written 4 times. I think that's what you were saying.
Yeah,
Yeah,
it turns out it's the same thing. Yes, it turns out it's the same thing, right? Because you're going to repeat the last prime for until you reach the next one. So yeah, you found a very very sophisticated, complicated way of saying this, but you're right. It's true. What you said is true. Yes, yeah, it's kind of cool. Yeah, okay. So I didn't see it that way, but it's the same thing. Yeah. So yeah, so you have 1 and then 2 and then 3. Now this is we've reached A4, right? And we just write down to 3 again. Then we reach 5. We write 5, 6, 7, 8, 9, 10, 11. So you see the pattern now is that you start writing that prime once you reach it. In other words, AN is the largest prime less or equal to n, right? If I start at 2, that's why the first one is annoying. But so AN is the largest prime up to that point. So for example, 19 is 19, right? Because 19 is prime. But A24, what's the largest prime up to that point? It's 23, right? And A12, so 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, that's 11, right? So it works, yeah. Okay. So that's one way, or by this other complicated way of seeing it, but it works too. Yeah, so that one is like sort of semi-tricky. F is cool. I won't do it. I'll leave it to you. A is pretty clear. I mean, you have to, I mean, if you look at them fast, I looked at them, I just looked at the sequence very, very quickly, like, half a second, I go like, no idea. But then you actually look at it, just play with it a little bit, and then it's, yeah, okay, I see it. But you really have to it's not like that, okay? Yeah, 49, I'll leave it to you guys. Okay, what time is it? Okay, 4.4. Okay, so now let's go to 4.4. And let's do, okay, where's in the, I'll do the one in the chat. So X7, I don't know if it's actually an exercise in the, okay, let's go to 4.4. Oh yeah, number 27. Yeah. No, I don't want to do that one now. Do I want to? Why does it have a star? Yes. Yeah. Okay. So I see. Yeah. So the problem with this one is that you can't apply the Chinese remainder theorem immediately because you see that, or directly, because 9, 12, and 21, they are not relatively prime pairwise. So you can't apply the Chinese remainder theorem as stated. Okay, let me just, so, okay. So number 27, careful. Careful. We're looking for x congruent to 7 mod 9, x congruent to 4 mod 12, and x congruent to 16 mod 21. I don't want to do this one now because I haven't even discussed the straightforward case. Okay, so cannot apply the Chinese remainder theorem because if you look at 9, 12, and 21, they're all divisible by 3, right? So 3 divides 9, 12, 21. Okay, so the theorem as stated does not apply. You cannot apply it. So you have to use something else. I mean, it might be possible to mess around with this to eventually use the Chinese remainder theorem, but it's not direct. Okay, so must use something else. And I don't want to discuss it now because I haven't even done the basic case. Okay, must use something else either completely or before. Yeah, for sure. Okay, so I don't know if I've assigned that one actually. It has a big fat star on it. So I did not assign it, but I mean, if you want, we can discuss it after individually, but I'd even have to think about it. I'll have to mess around with it. But yeah, that's a tough problem. Okay. So let's do. Okay, let's do, what the hell? Let's do number 11. And I'll need 5, but I'll do them. Okay, so let's start with number 5 in 4.4. B, 5B. Okay, so I'm asked to find an inverse of 19 mod 141. Yeah, it's just, yeah, so you have to be, it's just, of course you can try as many problems as you wish, obviously, but if I mean, I selected problems just because I'm trying to avoid certain things, but I mean, if you don't want to do it, you don't do it. If you want to really know about it, I'll explain it separately. Okay, so an inverse of 19 mod 141. Okay, so these are big enough that I'll have to use the Euclidean algorithm. So 141. So let's see. So 141, I divide by 19. Oh boy. The 7 fit? Feel free to give me the answer at any moment.
It's 7.
Yeah. Yes. Okay. So that's 133. And so that leaves 8. So the remainder is 8, right? So 7 times 19 plus 8. Is that okay? Okay. So then I repeat. 19, oh, we're lucky. That's 2 times 8 plus 3, or moderately lucky. 8 is 2 times 3 plus 2. 3 is 1 times 2 plus 1. And 2 is 2 times 1 plus 0. I stop. This is as expected. If I'm asked to find the inverse of 19 mod 141, the GCD had better be 1. Okay. So now what I want to do to find the inverse is Bezout, right? What does Bezout say? If, well, no, it says there exists S and T such that S times 19 plus T times 141 equals to 1, the GCD. Okay, so if you look at this S, it's an inverse of 19 mod 141, right? If I multiply these two numbers together, I get 1 plus a multiple of 141. Okay, so I want to find this S. How do I do that? Backtrack. Okay, so let's see. I've got one is I'm doing this live. I did not prepare this exercise. So if you catch a mistake, please just tell me, because otherwise we'll be in big trouble. So 1 is 3 minus 2. 1 times 3 plus minus 1 times 2. Then I go up. This is my first equation, second equation, third equation, fourth. This is using 1. Now I'll replace the 2. 1 times 3 plus minus 1 times 2 is 8 minus 2 times 3. So this is 3 times 3 plus minus 1 times 8. Yes, 9 minus 8. Then I'm going to use the third one. So 3 is 19 minus 2 times 8. So that's 3 times 1 times 19 plus minus 2 times 8 plus minus 1 times 8. So this is 3 times 19 plus minus 7 times 8. If you spot a mistake, tell me. Okay, and finally, the last one, we'll get 1 is 3 times 19 plus minus 7, and I replace the 8, it is 141 plus minus 7 times 19. So this is 52 times 19 plus minus 7. If somebody could just check that last line just to make sure it is correct. 52 times 19 minus 7 times 141. Is that 1? That's what you got. Excellent. Excellent. Okay, so 52 is what we're looking for. So 52 is the inverse of 19 mod 141. Okay. Now I'm jumping to problem 11a, where I'm going to use what I just computed. Okay, number 11a. Solve the following. 19x congruent to 4 mod 141. Okay, so we've got 19x congruent to 4 mod 141. Hint. So, okay, so you look at this and I said, congruence is just like equality. It's sort of a generalized kind of equality. So you have 19x equals to 4. What do you want to do? You want to multiply, you want to divide by 19, right? But you can't divide, we're not allowed to divide here. We can multiply by the inverse if there is such a thing. But yes, there is such a thing. There is 52. 52 is going to do exactly what we want, Okay, so now I can use this. So 52 times 19x will be congruent to, obviously, I mean, wait, let's do that. Okay, so 52 times 19x is congruent to 52 times 4 mod 141. That is always true. It doesn't depend on what I just did. What I did, though, tells me that 52 times 19 is the same as 1 mod 141. So this means that x is congruent to 52 times 4 mod 141. Okay, which is fine. You can leave it like that. But if you're asked to find, so find the smallest, or find x such that x is between 0 and 141, then you'll have to reduce 52 times 4, right? So 52 times 4, that is, well, I don't see much of a shortcut here. So that's 104 times 2. We could go to negatives, but what the hell? That's 208, and I'll just subtract 141. That's 7. That's 67. Hopefully, if I didn't make a mistake, that should be right. Yeah, if I didn't make a mistake, that should be right. Yes, that's powerful logic. Okay. So is 67 congruent to 208 mod 141? Looks okay. Everybody's gone. Okay, all right, next. We're almost done. Yeah. Okay, I'm not going to do an example of the Chinese remainder theorem now. I don't want to do it now. It's the end of the, we've done more than an hour. And we've got time. We're good on time. So, so I'll do another example next time. I'll just stop with that, unless you have suggestions, questions on actual stuff you want me to do now. Otherwise, I'll stop here, and I'll try to get the WebWorks out as soon as possible. And yeah, I'll do a little Google survey, because I'm really curious to what you guys are going to do next year, and then I'll set something up that you can, if you're interested in that little stagiaire thing, I'll send something out soon. Okay. Have you guys heard from universities yet? It's just
Only one.
yeah.
Concordia
Yeah.
is sending them out.
Okay. All right.
McGill has as well.
McGill, yeah.
Yeah.
I'm
Waterloo
taking
as well.
McGill.
Yeah. Okay. Yeah. This is about the time where things are
You've
happening.
heard back from Waterloo?
Yeah.
Oh man, this
Oh,
is not
that's
going to
good.
end well.
Well-
yeah, we all got in, didn't you?
No. They haven't answered for all programs yet. I got only 1 out of 2.
Okay.
Got an answer only 1 out of 2.
Okay.
L'Université de Montréal puis l'Université de Laval aussi.
Yeah, they don't all come out at the same rate. Please don't. I shouldn't have asked this. Sorry. Yeah. Okay. Let's stop this.